So to do that, let me open up this capture. Let me go to TCP capture. Let me take this IP of capture. So let me give TCP. So this is the filter we use in the Wireshark. So let me give you an glimpse about the options, what else we have. So all the customized template what I have created to have more insights on the fly. So this is the time when exactly the connection happened. This is the column where it defines about the time here. And this delta time we'll discuss in the class, but for the reference, delta time is very vital to understand where the problem is. So it's all mostly in milliseconds, but if it crosses the seconds, if you actually see this all milliseconds, this is 35 milliseconds, and this is 41 milliseconds. And if you see any values that's been incrementing here, that is defined as seconds. So in the networking world, everything is happening in milliseconds. If it exceeds the milliseconds, and if it's going beyond millisecond, and if it is in seconds, then there is a problem. That's a slow connection. So networking never like the packets to be in seconds, always. So for the optimal performance, it has to be in the limitation of milliseconds. So that's how this delta time value is used to figure out what is the time taken for the source and destination. So delta time, in one key thing I would say is we call this as a round trip time. Call this as RTT. Example, if you make a flight booking, that's something it will ask for. It's a one-way booking or it's a round trip booking. So that is something from source to destination, from destination to source. What is the time taken? That is bidirectional, from source to destination, from destination to source. How long it took? So that is actually a round trip time. We call this as an RTT. Even if in the ping request, you would see your RTT time. When you do ping, generally you can see your RTT. What is the average time taken is 7 milliseconds. That is your RTT. Your average time taken is 7 milliseconds from source to destination, back from the destination to source. That is your RTT. And then this particular field is talking about this as a layer 3, and you see all your IP packets here. So what is my source and what is my destination? This is the destination network where I'm trying to establish a connection. And this particular column will give a complete insights about what particular protocol is used by the source and destination. If you see here, it's my UDP. It can be a DNS or it can be a video streaming. That's how we can classify the packet. So here it says it's an UDP. And TCP segment length, we'll talk about that. We know, right, when we talk about this OSI model, we know about this. All in the network layer, we say it's packets. All it is IP packets. It's network layer. So from the layer 2 perspective, it's all frames. And from the transport layer, I'm going to send a packet using TCP or UDP. So this is all UDP packets, right? So that defines, it can be my DNS, it can be my video streaming. So we have to check how you will going to classify it using the port number. If you just click on this particular packet and you will drill down, you will see, okay, this is using UDP and this is a destination port is 53047. So this is not my DNS packet. This is something else. So here is your actual payload. Payload is something, your real data, right? So you will get about the insight about everything here. This is about what protocol I'm using. It will give you that. And TCP segment length. So we know in network layer, we say packets. In layer 2, we say frames. In the transport layer, we call this as a segments. Example, if I have a 1 GB file, So can I send this a one single file? Definitely not. So this 1 GB file is again chunked into multiple segments. So we call this as one segment. So for my one segment, how much maximum data I will send? That is your TCP segment length. What is the size of my segment? So, and one more thing here, the calculated window size. What is a window size? That is something like a proposal. So I'm proposing you, example, if I come down, drill down, little bit down, if you see my calculated window size. And this is very important. The maximum TCP, what is this TCP maximum segment length? It can be 14,440. And what is the calculated window size? So this is something, the proposal, it's saying that your window size never starts like this in the beginning. If you see the capture in the beginning, if you see this window sizes keep increasing. So when we establish a connection, it's not something like I'm going to, propose a biggest window size that you can send everything. So before establishing a connection, I should know what is the window size I'm proposing. So to do that, if I give TCP, and if you see number of displayed packets here, this is all my TCP packet here. Sorry for that. So this is the number of TCP packets alone I have filtered. And here I'm going to take this and I'm going to conversation filter and I'm going to TCP. So I have to do a right click on this and I'm going to conversation filter and I'm going to give TCP. So it has populated a default filter value here with this. So we got what all the information. It says as IP.address equal 192.168.0.104. That is my PC. And the destination is 117.102.109.18. This is the public IP address 186. And this is the port number used. What is my source port number? It's 53,333. So that is a randomly generated port number. This is generated by the operating system from our PC. And this is a server port 5201. So what is this particular capture? This particular capture is something I have captured this when there was a throughput issue. I had some problem. My PC had some problem with the throughput. So let's see how this window size exactly helps us to figure out the problem. Yeah, let's see that. So before that, so I want to go to the beginning, right? So where exactly my synchronization happened here. Let me little bit drill down this. This is actually the finished packet. I would actually see this TCP flow. It takes some time. Okay, this is the information I can see here. Okay, let me see. Conversation filter, TCP. It's a pretty big packet. I couldn't actually figure out. Okay, let me take a different capture. I want to see the SYN packet. Oh, I got stuck here. Okay, let me give TCP here. Okay. So here we go. So we got, SYN, SYNAC and ACK. It's talking about this 3-tuple connection, right? So this is from a client, this is a server, and it sends a SYN. The beginning before establishing a connection. So let's see. So if I take this particular packet here, if I open up my TCP, transmission control protocol, it says my source port number is 61918. That's my source. And this is a destination port. So from 443, I can figure out this is HTTPS. So now I come to know, okay, this is my source and this is my destination. And if I look at this IP protocol, I know this is my PC and destination is a public server. And if you see this, these are the key things we should know about, TCP. So I was talking about this sequence number. Since I'm not sending any kind of data at this point, so this is my first packet I'm going to send to this destination server. So this is the relative sequence number used by Wireshark. So this is the only value we are going to see. We are not going to see the, random sequence number here. So we are going to see this sequence number. And if you see the flags, this is what I'm talking about. So it says it's sync flag, right? So this is a sync packet, and this particular flag, it says it is sync flag. This is my sync packet. So from the server, what is the response we get from the server? If you see here, I made a filter for a granular control. There I can see all the information right away here. So here, if you see, the TTL is very important. The 3 default TTL values are 64, 128, and 255. And here my PC it's using something 64. That is something TTL is for every hop. Your TTL will be decremented, right? TTL is something for every hop. The value will be decremented. So example, this is 3 routers. So I know my internet connection, it has many BGP peering that happened in the middle that we call as an internet cloud. And I got my destination somewhere here, so it's all connected. And for every hop, the TTL will be decremented by 1. That's the logic. So here, if you see, I can definitely see the packets are routed and my routing is fine. So the sequence number is 0. And for this, the acknowledge number, what I get from the server is also 0. So what is the acknowledgement number? Actually, it looks like, so that's your actual data plus 1. That's your acknowledgement number always. So if you see here, the server responded back with a SYNAC, and for the SYNAC, my PC has been sent a SYN request back. And if you see the calculated window size, it started with the very least value, right? The default value 65,535, and that's been increased now. So I am proposing for 65,535 bytes. But now, since I established a connection, here we go, you send your real data, your payload. Here exactly your payload happens. And why this is important, that's a question here. Why I should know about all this? Definitely, because if there is a routing problem, I can figure out from the TTL, I can figure out, okay, this is a problem with routing. Straight away, I'm going to stop this. And if I see down, if I drill down, if my TTL is not decrementing, there is something problem with routing. So now I concluded, okay, this is not a problem with routing. This is something else, right? If you come down, the same way, the TTL is keep decrementing. If you see, here is your application data, exactly your application data, is being transferred here. Your real data is transferred here. And if you keep drill down here, your application data exchanges keep happening here. So when I stop here exactly, okay, I come to know, okay, this is a TCP retransmission and this packet is push packet. How I know about push packets, if you see the flag here for this particular packet, this push packet is set. Okay, I'll discuss about this. So the flags are very important, and mostly in my experience, and always these three parameters are widely used in most of the time, the TCP flags. One is the key thing is the SYN packet, SYN flag, and then push acknowledgement fin. Believe me, these four are the key flags that most commonly used, and we are so much interested to know about only these four most of the time, I would say. So it will not go beyond that. So push is something here, I would say the push is something, see, it generally happens when the connection is about to close the data transfer. So example, if you send a sequence number and if you send a SYN and you get a SYNAC back from the server, for that I'll send a acknowledgement again. So here your actual data transfer is happening, right? Here your application data happening, and for every single conversation I got an unique sequence number. And this particular application data transfer is happening between source and destination. And when it is about to set this fin flag, it's about the push. Hey, you don't worry about that. You keep receiving my data. We are going to finish this traffic. I mean, we are about to end this conversation. This is, a couple of bytes that's left out from me. So I'm going to push this packet you're going to receive. And exactly here, the problem happened, right? So for the push packet, it's asking for the retransmission. Why the retransmission happens? It says, you're going to push your data, but I haven't received your traffic, what you sent before. So here comes the role of sequence number. So this particular sequence number, for that, I didn't get the data for 33026, exactly a packet before this. If you see, the calculated window size is same. And if you see, my calculated window size is not increasing, and it is asking for the retransmission. Why the window size is not suddenly it's dropped to 82,944. Earlier this is 2,62,144. That is because I'm not ready to receive your data. You might be fast enough to send your data, but I have a problem here. You have to send your data slower because I cannot process your data. So the retransmission, TCP, duplicate acknowledgement, this all happens because of throughput issues. So this is one kind of scenario where I captured. This is, if you see a lot of fast retransmission, out of order, and all this TCP errors is happening because of a throughput issue. I'm dropping a packets here. So this is the level of detail you get from Wireshark. So inside the TCP, we have different parameter. This is one quick glimpse, and I gave you what is this window size and how we rule out this window size problem, right? And I'll show you one more scenario where we had a throughput issue with a different scenario. I'll close this connection and let me open up this. Okay. So before that, let me give you insight about how exactly we should capture this throughput issue. So I would suggest that there is a tool called iPerf. It is a very most widely used tool by the network administrator to find the bandwidth. So before that, I'll give again an overview of what is bandwidth, what is throughput, what is speed. So my when I started a career, I had this confusion. So what people are talking about bandwidth, throughput, and speed, what exactly the key difference between all these three? And what it really matters here in Wireshark? Definitely, yes, we should know about all that here. So bandwidth example, if you got a link here and you have connected to your ISP and this is your switch, router, anything that's connected here, this is all end user PCs. So you got your 100 Mbps link. at least line connection, guaranteed bandwidth, 100 Mbps. So this particular parameter, we call this as a bandwidth. So they say it's something problem with your bandwidth, and you have some performance issue that's happening here. So how you figure out that? You have to bypass your router. I mean, what I mean about bypass is something, I should not use a router. Instead, this particular connection that's coming from the ISP, I have to connect to my laptop, and I should do a capture, and I should see if any retransmission is happening, like before we have seen, right? Sorry for that, let me write it clearly. So I should see if I see any kind of retransmissions. So I have to figure out that. So before that, using the iperf tool, I did a capture here, the iperf tool. So where I want to show you exactly where this window problem happened. If I come back here, this is a reset. So there is a particular filter to figure out this. If you actually see here, see, this is the fin packet where exactly my communication, successfully terminated on both ends. So when fin packet exactly happens, this is a client and this is a server. Right? So when there is a successful connection, it has to send a SYN packet, and for that SYN, it has to send a SYNAC pack, and it will send a acknowledgement for the SYNAC. This is a common scenario where this particular fax comes in here. I told you push happens before the fin, and fin is something I agree for that. I got all the data in this particular segment. I'm talking about the segment, this particular segment. I got 64 bytes. I got all the data. I am fine. I'm good to close the connection, and it's going to set this fin flag set inside TCP from the source. And the same way in the destination, it's going to send a fin packet here. It's a mutual agreement to terminate the connection, to close down the connection from the source and destination. It's something like, you are talking to your friend in the phone call and say, hey, I'm done with my conversation, let me disconnect. That's a mutual understanding between source and destination. So that's how this fin comes here. So why there is a problem with, what is this packet coloring is red? Because this is a reset. Why it is a reset? I didn't get your packet. It's abruptly disconnecting a connection. So my TCP conversation is happening here. And who is doing this reset? That's a key thing you have to figure out, okay, where there is a problem with the throughput. So if you exactly see, this is my source PC and this is a destination. And here exactly, if you see, calculated window size is 0. I'm going to reset this connection. I'm not going to propose anything because I am not ready to receive anything because I didn't get the previous packet. So I'm going to reset this connection. This connection is not successful. If you see a lot of reset packets in your network, then definitely it's a problem. But the key thing is where exactly this is happening. That's important. If you see my IPv4 IP address here, this is 192.168.0.104. This is private IP and this is public IP range 152. And if you see the TCP segment length for all the reset packets, it's all 0. If you see the acknowledgements also, I'm not acknowledging your actual segment length. This is something problem. So the real data exchange is not happening at this point. So all this red priorities and there's alarm signals that indicates that there is a problem. But why Wireshark is very helpful at this point, I can figure out where exactly this happened. This is what exactly I'm trying to find. See if this is something I am proposing. I am saying that My TCP window is full. You don't send any kind of data. If you see after this particular conversation, this is from the client to server. So here we have to see, this is very important. So if I see the client, I got 3 resets. So all happened because of my PC. And along with that, this is the destination. And this is the calculated window size. And this is the sequence number. See, and this is my TCP window is full. It's saying you don't send any data. I'm not ready to receive because my TCP window is full. TCP window specified by the receiver is now completely full. You don't send any data. I'm full. So now I can figure out, okay, this is something problem with my connection. At some point, I'm dropping packets. I cannot process a packet. But even though the server is ready to send the data, but I cannot send because my TCP window is full. I cannot receive any more data. This is some kind of proposal, some warning it says. So now I can go ahead and say, hey, yeah, I agree. It is something problem with my PC. I have to look into this PC. Why it can happen? Maybe this particular PC might have established multiple connections to the internet and it cannot process the packet. Right? So my particular throughput is low. What is throughput here? So when we discussed about bandwidth, I explained what is bandwidth. That is your actual link speed is your bandwidth. The throughput is something how much I get out of the bandwidth. But how I know what is the throughput I get for my PC? So if we go back, let me try to bring up the iPuff tool here. Sometimes this public iPuff tool is always busy. I have to give iPuff. So here I got my iPuff. Let me open up my iPuff here. Open path. Going to copy this path. Open in terminal. Okay, I'm on this, and if I give dir iPuff-c, and there are many iPuff servers that you can test. I'll tell you what is an iPuff server. So we'll do iPuff testing. So let me check DNS flow here. DNS. This is a place where exactly I did an iPuff for a public server. Okay, so now I'm connected. So they say you got 100 Mbps link. So here are the key things we have to understand here. So we'll see what is the throughput. Okay. See per second, what is the throughput I get here? So this is the guaranteed bandwidth. So I got 100 Mbps link, and how much I can send per PC. This particular PC can send, this particular speed for this PC. You got it, right? This is a guaranteed bandwidth, 100 Mbps, but that particular 100 Mbps is not completely given for my PC. It's a shared bandwidth. So now I have connected my computer, my TV is consuming a few bandwidth, and my mobile is consuming few bandwidth, and my laptop, and I got a guaranteed bandwidth, and this is the throughput. I can send 21.9 MB per second. So how much data I have sent here is 2.62 megabytes. And it is the interval is between every second I'm sending this data. So this is your average data sent, and this is your average throughput. And one point of time where my PC, it says, hey, my TCP window size is full. You don't send any data. until I process this packet and I'll send out a new proposal where I know I'll propose the new window size, and then after after that you can send your data back and I'm ready to receive. So but at this point of time, no, my window size is full. So that is the use of window size. That's why we should know about window size. So where is the problem? So here my bandwidth is fine, my transfer rate is fine, my internet is fine, but I come to know it's because of the TCP. Since my window size is full, I cannot process a packet. I'm busy with other connection, established connection. Yeah, this is about real-time scenario where we often experience this problem. That's something people they keep barking about, this throughput issues. So you can make use of iPerf, and when I did an iPerf, this is a capture I exactly did, and where exactly it said that okay, my PC is proposed a window size. It says, hey, I am full. You don't send anything because my TCP window is full. Here you can see my calculated window size here, it is full. Yeah, that's it about the throughput issue. You have more details in the real classes. This is one scenario. We have so many interesting topics like how we do the same for UDP traffic, and every packet, it's guaranteed you can definitely figure out where exactly the problem is. If you see here, it proves again, I got a TCP window full error again from my client. It's very visible. It's my PC. It's my PC. It's not about the bandwidth. This is something I have many connections running. So from there, I have to drill down what is the problem. So the problem is what is the biggest takeaway of this scenario is you can figure out exactly where the problem is. That's the root cause, and we always have problem in finding that. We don't know where is the root cause, and you're rattling around to find where exactly the problem is. The root cause is the main thing. So from there we have to dig deeper and figure out why this particular PC is proposing a TCP window size as in it says I am full, you don't send any data. Why is that? Is it my connection is too busy or my network is too busy? So I can start looking at from my PC perspective now. So I don't want to rattle around. It could be a problem with my internet link. No, it's all clean. So this is all about the throughput and a quick overview about MTU and MSS. So this is a major confusion. Many people they have, even I had questions 4 or 5 years back. What is the difference between MSS and MTU? MTU is maximum transmission unit. It comes under your Ethernet header. The maximum value is 1500 bytes. Why this is important? Let's discuss about. So maximum segment size is for TCP. What is your maximum segment size? There is a limitation for it. So I'll give you a visual about how it looks like from the Wireshark perspective. Let me go to MTU. So MTU is layer 2 and it has to match. See, if you have set your MTU as 1500, if you see here, if there is an MTU mismatch, your connection is not going to happen. So you can find everything in Wireshark. How do we find an MTU mismatch? And if you see here, this MSS, maximum segment size, is on TCP. Some TCP layer. And if you see the maximum transmission unit, 1500 bytes, and it's in the layer 2 Ethernet header. And people from networking background, they might encounter this. I mean, they would adjust the MSS value in the GRE header. So generally in the IP header, I'll give an insight. And inside in the IP header, right, inside the IP header, there is one more header is called GRE header. Why this is used? Because if I want because my IP packets is 20 bytes, and if I add this GRE header, it's a 2 byte and additional information, I cannot exchange this data, because my actual packet size will be incremented and it cannot be routed back. So what I'm going to do here, so I'm going to decrement my payload. How to decrement the payload? So I am giving some part of bytes to GRE header. So that's the reason you do this IP MSS adjust command in your router, and you will decrement the value something like 1260. So generally it will look something like 1460 default. So if you see this particular 1500 is the MTU, but the maximum segment length, as I said, TCP and IP header is a 20 byte each, and it consumes 24 bytes extra, and your packet cannot be routed back. So you from your actual payload, they'll decrement this. So that's the reason the actual payloads comes here, maximum segment size, and here we have to borrow some bytes. So we are freeing up some space in the segment size, and you're going to route your traffic. And now the GRE packet has been forwarded without any problem. So that is something you have to adjust your MSS segment size, your payload traffic, that should be reduced a bit from your default value, so that that particular space will be used for the GRE header. So that's it about MTU and MSS. So I'm done with my presentation.